네, 정상목 씨 안녕하세요. 박건우 씨 안녕하세요. 네, 한성민 씨도 안녕하세요. 네, 자, 오늘 수업 시작하기 전에 여러분들 그 숙제 어땠는지 한번 이야기를 듣고 시작을 하도록 하죠. 네, 여러분 일단 호목에 대한 얘기를 먼저 하시고요. 그 다음에 질문을 해주셨으면 좋겠습니다. 세 분 모두 호목을 하는데 어떤 어려움이 있었는지에 대해서 먼저 말씀을 해주시겠어요? 자, 네. 여러분들이 호모지니어스 샘플에 대해서 이제 수행을 했다고 하는데 어떤 것들을 해보신 건가요? 이렇게 호모지니어스한 바가 있다고 칩시다. 자, 이 상황에서 여러분들이 어떤 일을 하신 거죠? 여기서 어떤 익사이테이션을 주셨나요? 그러니까 익사이테이션이 여러 가지 종류가 있을 수 있잖아요. 포화성 방정식 혹은 전자, 홀 이렇게를 건드려 볼 수 있을 텐데, 자, 이 중에서 어떤 거를 지금 바꾸셨죠? 어디에 퍼터베이션을 넣었는지를 질문을 드리고 있습니다. 선택이 있고, 일렉트론과 홀 컨티뉴이티에 익사이테이션을 주고 그 다음에 어노드와 캐소드에서 계산을 해 보았다. 네. 자, 그래요. 그러면 이런 케이스를 하나 생각을 해볼까요? 바로 요 지점이 우리의 소스가 존재하는 지점이라고 생각을 해볼까요? 네. 그리고는 각 터미널에서의 전류를 계산을 했어요. 이렇게 이쪽 방향. 그러니까 예를 들어서 델타 I 캐소드를 계산을 해줬을 거고 델타 I의 어노드를 계산을 하셨을 겁니다. 자, 그 다음에 어떻게 이것이 맞다는 거를 판단을 하셨죠? 자, 여러분들이 다 비슷한 방식으로 검증을 하신 것 같은데요. 자, 생각을 해보면, 그렇죠. 여러분들이 검증을 하셨다는 게 이런 거지 않겠습니까? 그러니까 이제 전류 중에서는 성분들이 여러 개가 있을 텐데, 예를 들어서 그 디스플레이스먼트 커런트에 해당하는 캐소드의 디스플레이스먼트 커런트하고 그 다음에 캐소드의 어노드에 해당하는 디스플레이스먼트 커런트의 합을 구하셔서 그것이 차지의 변화와 관계가 있다는 것을 얘기를 하신 거죠. 자, 근데 이 식의 근원이 뭔지를 한번 생각을 해보세요. 이 식의 근원은 이와 같은 식이죠. 이렇게 돼 있을 거고, 요거를 시간에 대해서 미분을 하게 되면 이렇게 이와 같은 식이 나오게 될 거고, 자, 그래서 우리가 이거를 디스플레이스먼트의 시간에 대한 변화율을 디스플레이스먼트 커런트 덴시티라고 부르니까 이와 같이 될 거고, 자, 그거를 이제 볼륨에 대해서 한번 적분을 해볼까요? 자, 이렇게 적분을 해보면 이 적분은 이제 다이버전스 정리에 따라서 변형이 되겠죠. 이렇게 디스플레이스먼트 커런트를 바로 모든 면에 대해서 적분을 해주는 것이 될 겁니다. 이거를 다 적분을 하고 나면 사실 우리가 생각할 수 있는 것들은 요 간단한 예제에서는 면이 4개가 있을 거예요. 요 노란색으로 표기한 면하고, 그다음에 이쪽 컨택이 아닌 이런 면 2개가 있을 텐데, 우리가 호모지니어스한 노이만 바운더리 컨디션을 사용을 하고 있기 때문에 이게 사실은 어떻게 바뀔 수 있냐면, 적분을 하는데 디스플레이스먼트 커런트를 적분을 하는데 바로 캐소드에 대한 적분과 이렇게 어노드에 대한 적분을 하실 수 있을 거예요. 자, 그러면 이걸 우리가 뭐라고 부릅니까? 요거 요 값에 해당하는 것이 바로 마이너스의 디스플레이스먼트, 캐소드 쪽에서 바라본 디스플레이스먼트 커런트가 되겠죠. 그리고 요 두 번째 항이 뭐가 될까요? 요게 바로 어노드 쪽에서 바라본 디스플레이스먼트 커런트 성분이 될 겁니다. 그리고 그것은 우리가 요 식에서 이렇게 가는 것이 다른 게 아니라 단순한 적분에 불과했으니까 결국 우변은 어떤 식으로 나타나게 될 거냐면 라운드 t를 시간에 대해서 적분을 해준 것일 거고, 요것은 결국은 시간 미분을 바깥에 빼고 나면 이렇게가 되겠죠. 그래서 여러분들이 이거를 예를 들어서 뭐라고 정의를 했는지 모르지만 예를 들어서 Q라고 했다고 칩시다. 그러면 이런 관계식을 통해서 이렇게 이런 식을 쓸 수 있다고 해보죠. 자, 여기까지 수업을 들으시는 분들 모두 다 이해를 하셨을 거고, 그걸 이용을 해가지고 그림 펑션이 올바로 구해졌는지 안 구해졌는지에 대해 가지고 생각을 했을 거예요. 자, 그런데 여러분, 여러분들이 확인한 게 뭐죠? 그러니까 결국 무슨 식을 확인을 하셨는 거죠? 여러분들이 여기서 확인한 식이라는 것은 바로 우리가 포화송 이퀘이션이라고 부르는 이 방정식을 지금 검증을 하신 거예요. 포화송 방정식이 올바르게 구현이 되고 있다면 이 관계식이 만족이 되겠죠. 근데 그러면 만약에 컨티뉴이티 이퀘이션이 잘못 계산이 되고 있다면 어떻게 되겠습니까? 그렇다고 해가지고 이 관계식 자체가, 제가 박스로 이렇게 친 관계식 자체가 달라질까요? 그러니까 여러분들이 확인한 것은 퍼터베이션을 주었을 때 거기에 대한 포화송 방정식의 응답이 포화송 방정식 자체로서는 잘 계산이 되고 있다라는 것을 말할 수는 있겠죠. 그렇지만 그거 말고 우리가 고려해야 되는 다른 방정식들에 대해 가지고는 좀 더 생각을 해보셨으면 좋겠습니다. 자, 그렇게 하고요. 그 다음에 질문이 있는 분들은 질문을, 박건우 씨가 질문이 있다고 그랬던 것 같은데요. 질문을 해주시고, 없으면 이제 강의를 시작을 하도록 할게요. 자, 박건우 씨 질문에서 컨택이라는 것이 소스하고 드레인 컨택을 말하는 거겠죠. 그러면 소스랑 드레인 컨택은 컨택을 어떻게 잡았느냐에 따라서 다를 텐데, 예를 들어서 제가 예상하는 바는 이와 같이, 예를 들어서 이게 실리콘이고 이 위가 옥사이드고 이 밑이 옥사이드면 박건우 씨가 예를 들어서 이와 같이 이렇게 컨택을 설정을 했다고 생각을 해보겠습니다. 자, 그리고 나면 여기에 이제 점들이 존재하게 될 텐데, 뭐 요런 노드들이 존재를 하겠죠. 이렇게. 자, 커런트를 우리가 DC 상태에서 생각을 해줄 때 당연히 이렇게 생각을 해서 실제로는 이쪽 플럭스가 중요하게 될 겁니다. 여기를 통과하는 이 플럭스가. 물론 그리고 이 플럭스는 실리콘 영역을 통해서만 들어오겠죠. 왜냐면 옥사이드에서는 우리가 캐리어가 없으니까요. 그런데 AC를 생각을 한다고 하면, 그러면 심지어는 요런 상황이라든지 혹은 여기서 이렇게 가는 상황이라든지 같은 것들도 사실은 디스플레이스먼트 커런트를 기여를 할 수가 있게 되죠. 그래서 이런 부분들도 당연히 계산을 해 주셔야 되는 거고요. 이건 사실 AC를 할 때 이미 했었어야 되는 부분이죠. AC를 생각을 할 때 이미 고려가 되었어야 되는 부분이고요. 그렇습니다. 자, 또 다른 질문 있나요? 네. 네, 알겠습니다. 자, 그러면은 오늘 강의를 계속 하도록 할게요. Okay, this is lecture 22nd. So we have, I guess we have 5 remaining lectures. So including today's lecture. So let's proceed. So right now, so I guess that current situation of your code development is not as fast as I expected. So in homework, so I ask you to calculate the green function for terminal current. For example, this is anode, this is cathode, okay. This is terminal current green function. So have you all calculated the current green, terminal current green function too? Terminal current green function. So from your response to my previous questions, I can understand now you can calculate the quantities like so alpha, beta, and r and r prime. Now you can consider the response of your physical variables like potential, electron density, or hole density with respect to a perturbation occurring at a position of r prime. So I know it, but my question is, so have you tried to calculate the terminal current out of it? So we are now talking about this terminal current green function. So today's lecture was actually intended to give you an efficient way to calculate this terminal current green function. That is one important subject we will consider, but I'm afraid that actually none of you are actually can calculate the terminal current green function accurately. So so I'm afraid that if I go further, then maybe you are lost in our lecture progress. So so I wanted to change my lecture plan. So originally lecture 22 was devoted to the efficient way to calculate terminal current green function, but instead of that, let's consider another topic we can consider in this course. Okay, so are you with me? So everybody, please state your current code development. So have you all succeeded to calculate the terminal current green function, or you are still struggling with the code development? So please let me know. Mm-hmm. Okay, so when you say code, so I'm specifically asking you the capability to calculate terminal current green function. So once again, I wanted to ask you whether you can calculate not the general green function we can define in the diffusion model, but instead of that. So please implement a capability to calculate terminal current green function out of it. Okay, so please check whether your calculation is correct or not. Okay, so I wanted to postpone this further development of our terminal current green function theory. So not theory, but anyway, quick way to calculate it. So that will be discussed in later lecture. So if you, when I feel that you are ready to discuss about that uh, topic, then I will come back to this very important topic. Okay, so please, for a while, please develop, please please try to develop a correct code for your terminal current green function. So then, instead of today's planned lecture topic, so I just wanted to quick lecture or short lecture on other topic, which can be found in the computational microelectronics. So that one is so-called trap, implementation of a trap inside our diffusion solver. That will be the topic of today's short lecture. Okay, so up to now we have simulated our code with, for example, just three equations. That is the basic form of a drift diffusion model. So in this case, we can consider Poisson equation, which describes the electric field, and electron continuity equation, and Hall continuity equation. Those equations are used to describe the status of our system. So it is basically means that yes, electric field is an important quantity and electron density is an important quantity. Also, Hall is an important quantity. That is basic underlying assumption about our adoption of these three equations. But you know, sometimes we are interested with the things called trap. So of course, trap means that something to be installed to catch an animal or an enemy. So if your target is moving here, then you can make a trap here. Simple. That is a trap, and that is just hidden, and as if that is just a normal ground. And if your target is approaching, and when it is captured, then what will happen? This guy will be now captured by this trap, and let's say this is written as A, then later you will have A captured by this trap. So very similarly with this description about hunting an animal, so we say that trap for our electronic charge carrier. So for example, this trap means that certain state to catch our electrons or holes. That is the meaning of naming called a trap. So that is an analogy with such kind of situation, animal hunting. Okay, so simply speaking, we are now saying that in semiconductor we have two bands. Okay, so conduction band and valence band. Of course, sometimes we can think that the conduction band has many bands in it. So especially when you consider silicon, although we say that silicon conduction band, but actually it has a little complicated internal structure. So at least in advanced Monte Carlo simulation code, we can define four different conduction bands. So starting from this minimum and another minimum, that minimum, and that minimum. Of course, they are so closely related, so we believe that the electron located here can be fully moved into this higher and higher bands without any difficulty. So through the free streaming, they can arrive at higher bands. So that's the reason why, although we have multiple conduction bands, but they are all regarded as a single body. Quite similarly, also you know that, and even in this valence band, we can find many different whole bands. For example, heavy whole bands, light whole bands, and split of whole bands. There are many of them, but they are all merged into just or sometimes treated as a single body, although they are energetically different and separated. So anyway, our description is like this. So there are a lot of states here, and there are a lot of states here. Even inside these states or these bands, we can find several internal structure. But point is, whether that is effective in its effective mass, sometimes it can be heavy or sometimes it can be light, and there are many different things we have to consider. But anyway, if we apply certain electric field and try to move its position in the k space, momentum space, then yes, changing it is in principle possible between or inside the conduction band and inside the valence band. But you know that, so sometimes if we have the imperfection in our silicon crystal, then maybe we will have a certain energy level which are not quite much related with this conduction band and valence band. So we have considerable difference, energetic difference. Yes, here, yes. So here we have a certain defect level, and this defect level is distinctively found in from EC and EV. So we have no way to place our electron originally occupying certain state in this region, this energetic position, into here by applying certain electric field, or yes, so we cannot move our electron into this way. Or even for our silicon valence band, there is no way for us to move our electron into this one by just applying our electric field. So the reason why we can move our electron inside the conduction band is like this. So let's say that this is K and this is energy. So in principle, we have this uh, distinctive values for momentum and crystal momentum, and then we have certain energy value corresponding to certain momentum value, and also we have a certain energy value corresponding certain momentum value. That is the dispersion relation, so or EK relation of our conduction band. So if we apply the force into certain particle occupying this position, then by applying the force we can change its momentum, and we can change its electric field. So since they are so closely related smoothly, so we by applying certain force, in this sense electric field, we can move in it. However, so simply speaking, the states in located in this part are well connected through these lines. However, unfortunately, between the conduction band and defect level, and between the defect level and balance band state, we cannot find any meaningful lines connecting them all. For example, if you are working in the conduction band, then when you slightly change your momentum, then you can find certain related energy value. You can find it. However, so they means that this conduction band stays, and for example, this defect level are so much separated, so just uh, changing, so we cannot make any interaction between this and that. It's not possible. By applying certain force, we cannot move that into here, so that's not possible. So up to now I have just explained why our defect level separated, energetically separated from conduction band and valence band cannot be achieved by just normal transport. So the normal transport means that when we apply certain force, then our crystal momentum is changed, and also energy is changed. However, in this defect level, that is very much separated from these lines for EK lines for EC and valence band and conduction band. So by just applying certain force, we cannot place our electron into the defect level. So then maybe you can think that this defect level is always empty, or however it's not. So although not directly accessible by the electric field, but we have many other means to fill out this defect level. For example, let's say that this is located around the mid gap of our silicon band gap, then roughly say that this would be just so half of our band gap, and also half of our band gap. So let's say that there is a certain defect level, and how can we just fill it? Um, so quite easily, when you have zero temperature, absolutely zero temperature, then even this conduction band is not occupied, so that it becomes really completely empty. So then usual explanation is, when you increase your temperature little bit, then what happens? So previously there were electrons, and some of them quite a lucky electrons, so just to jump into here and it will occupy a previously empty state in the conduction band. So if we are living at around, for example, 300 Kelvin, then there is quite a small but non-negligible amount of electrons located here. So you know that in this case, these electrons are winner of overcoming the band gap. So band gap is overcome by this electron. However, when you consider this defect level, the barrier energetic difference for our electron is just half of it. So simply speaking, if we can find certain non-zero electron density inside our conduction band, it means that even more electrons can be found in this defect level, because this is a much easier problem for our electrons located in the holes. So from the viewpoint of our hole, so our electrons occupying the valence band, so they have two choices, just to overcoming the band gap and occupying the conduction band. And another route is just taking the defect level that is far from just half band gap. So what will be the preferred way? Of course, yes, this one is much easier for our electrons. So we can expect that the occupancy, the probability of a single defect level is occupied will be much larger than the occupancy of our conduction band. Okay, so simply speaking, now you all know that even in this case, even when we insert defect level, at equilibrium, we will have the Fermi-Dirac distribution. So simply speaking, so at a given temperature, and let's say that this is happen to be, for example, Fermi level of our system, then you know that at this Fermi level we have half of occupancy, and we will have, yes, this form, which is quite much vanishing, almost close to 0 here, and almost close to 1 here. And you know that there is just a few kBT energy, so summer energy, to have rapid transition from full occupancy to almost no occupancy here. So now you understand, if we introduce a defect level inside our silicon crystal structure, so then at equilibrium case, yes, there can be certain amount of electrons occupying this defect level, and also we will have a certain amount of electron occupying this conduction band level. Yes, that's it. So then what will be the effect of this additional state? So if we have this additional state, then we can find two different effects of this state. One is in the Poisson equation. So think about this one. When you have a Poisson equation, so you have to define rho, so net charge density. And when you consider net charge density, for example, you consider so positively charged hole and negatively charged electron, and you know here you have certain, yes, so net yes, you have this one. So if you have donors, then that will be positively charged, and yes, So if you have acceptors, then you will have a negatively charged one. So this was the previous treatment for our Poisson equation. So you know this quite well. However, now you have, for example, this additional defect level. Yes, now it has additional electrons taking this defect level. Then when you calculate the Poisson equation and when you consider the net charge density, then you have to also consider the contribution from these additional electrons occupying the defect level. So they are called as NT usually. T sometimes it can be written as small letter or capital letter or explicitly says a trap or anything. So anyway, you can understand this guy represent the amount of electrons occupying the defect levels. Okay, so up to now, do you have any question on this trap? So this defect level is called as trap. Why it is called as trap, that will be explained soon after. But for a while, I'm just asking you whether you have all understood the explanation up to now. Okay, good. So now you have this trapped charge. Of course, then you may ask that this one, if we don't have any trap or any trapped electron, then yes, contribution is really zero. Yes, yes, when we have no trapped charge, trapped electron here, then of course we will have a zero contribution from this mobile carrier. However, also you may or may not have additional term about the background charge for your state. For example, there can be a certain defect level which is neutral only when it is occupied by an electron, or there can be another one it becomes neutral when it does not when it is not occupied by an electron. So depending on the property of this trap level, then there can be the background level for our net charge density. So that is one note on that. So you may have something constant number for it. So that was related with the Poisson equation, and we also have to consider another equation. So Poisson equation, why we have to consider this guy, this trap in the Poisson equation? Because yes, it can have or have not the charged particle called an electron. So when it consume or capture the electron, then it will be, for example, negative charged, and if it release or if it emit the electron, to capture the electron, then it becomes, for example, neutral. So therefore, that introduces a change in your net charge density. Yes, so we have to consider the trap in our Poisson equation. But more importantly, so another thing we have to consider is the occupancy itself. So n sub t. Who decided this n sub t? So of course, at equilibrium, if we are working equilibrium condition, then this nt will be simply given by the Fermi-Dirac distribution. Of course, not exactly Fermi-Dirac. You know, the Fermi-Dirac distribution is just a unitless number. So n sub t is typically written as per cubic centimeter. So that is nt is at equilibrium, simply given by the total number of trap multiplied by our trap occupancy. So this trap occupancy of course follows the Fermi-Dirac distribution, and nt at a certain position, how many defect levels are there, that is really material dependent parameter. So material means that when you prepare your silicon wafer or when you process on that wafer, so you can introduce many different defect levels, and by applying certain heat you can cure and remove many of them. So whether you will have many traps or many defects or less defects, almost no defects, that really depends on your situation. So although, for example, conduction band and balance band, that is really almost universal for every device simulation, as much as you use the silicon material. However, this NT, the trap density, is really depends on your specific application, your fab. So that is one degree of freedom which should be found out by our ticket users. Of course, this Fermi-Dirac distribution is quite well known, and that is just a function of your trap energy level. So, for example, if your defect level or trap level is located quite close to your balance band, then maybe you will have a higher FT value. And if we locate our trap quite close to the conduction band minimum, then what will happen? Then we will have a very low value for our trap occupancy. That is quite easy and really accessible. However, this is only valid for when we have the equilibrium case. So if we don't have equilibrium case, then actually the electron density and hole density can be far from the equilibrium values. So accordingly, so there is no guarantee that our defect level follows also the equilibrium distribution. So then obviously, if you have this non-equilibrium case, what should you do? So as like a conduction band electron or valence band holes, you have to introduce additional equation for your n sub t. That is my point. So when you consider the conduction band electron or valence band holes, usually what you do is just to specify the dynamics of your interested quantity. how the conduction band electron density change when we have a certain physical effect, or how our valence band hole density changes with respect to time when we have a certain physical effect. So now you can imagine that the equation we have to introduce in this position will be simply given by what happens if we change something, then what will happen to our trapped electron density. That equation is required. In the case of electrons and holes, the most significant effect we have to consider was transport. So transport means that the change of its motion or change of its position with respect to the time. So we have to consider, for example, this guy previously we had. So time derivative of electron density is directly related with the outgoing flux. Actually, the outgoing flux introduces net loss of electrons. Also, outgoing flux of our hole, that is directly related with loss of holes at a certain position. Then maybe you are now trying to say, okay, maybe I can introduce such a kind of thing, but you know that it's not possible. There is nothing like that. Yes. There is nothing like that. Oh, because you know traps are just highly localized at a certain position. So think about what is the trap and what is the conduction band. Conduction bands, so that is just chain of connected, well connected silicon atoms. So it can freely move over those silicon atoms. However, in the case of a trap, that is highly localized at a certain position and it cannot escape from that specific location. So motion of a trapped charge, trapped electron is not applicable. So instead of that, we have nothing here. Then what is then remaining way for our trap can have electron or don't have the electron? So that is just localized movement of our electrons. For example, our electrons originally located at this defect level can be moved into conduction band or moved down to valence band, or the electron originally occupying this conduction band can move into this defect level, or the electron occupying this valence level state can move into the defect level. So there can be 4 different transitions we can consider. Of course, all of these 4 transitions, yes, they are called transitions. Transitions occurs at a specific point, so around the defect level. So that is not related with positional or spatial change of our electron. Electron is just located there. However, its energetic position is changed. Okay, so maybe you can easily understand this one. So now we have to introduce here additional term not related with spatial change, and we have to consider transitions in it. Then what happens? Let me just describe this equation. If we have, for example, electronic motion from trap state to conduction band state, then what will happen? That will negatively contribute to our trap density. You know it. And if we have trap to balance band transition, of course, that will have negative impact on the trap density. And also, when you consider from conduction band to trap transition, that is influx of electrons into the trap level. That is welcome. So we will have positive value. Also, if we have from balance to trap level transition of electrons, of course, not holes, but electrons, then we will have also positive contribution to our trap density. Yes, that is 4 possible contribution from our electrons. And yes. Then now when we introduce such kind of transition, then at the same time our continuity equations for electrons and holes should be modified. For example, let's say that there occurs one transition from trap to conduction band. Okay, that is the loss of electron from the viewpoint of our trap. However, from the viewpoint of our, how can I say, yes, conduction band, yes, this transition is a welcomed one. So from trap to conduction band, that is counted as in a positive way. Okay, from the defect state, one electron is moved into our conduction band. Okay, now electron density is increased. And if we have conduction band to trap transition, then although that is counted as positive in our trap density, but at the same time from electron density, that is regarded as negative event for it. Okay, so now also consider this guy. So another one is, now we have to a little bit careful about that. So now we consider the transition of electrons from trap to valence band. That is shown here. Then what will happen? So this one now considers the moving out electrons, and let's say that this from the valence band case, there was a certain hole, an empty space inside the conduction band, but that electron previously occupying the defect level is now moved down into valence level, and that previously empty level is now occupied by our electron. So in this case, yes, we have to consider once again negatively to this trap to valence transition. On the other hand, if we consider this transition, so movement of electrons, from balance band to the defect level, then that is, yes, counted as positively for our trap. Also, since one electron is moving out, a hole is generated. So now we will say that this is corresponding to this way. So don't be confused with these different signs. It is simply because we are talking about electron and holes, not state, uh, not the electrons occupying the valence band itself. Instead of that, we are just talking about the number or density of empty states in our valence band. So that's the reason why we have different signs here, but you can manage the correct sign for all of them. So simply speaking, yes, this is the electric picture, and this one is written as also in electric picture. However, it is in a whole picture, so that's the reason why we have different signs. Okay, so how about your understanding on this equation? So now, although we have not thought about the exact form of transitions, so trap to conduction band or conduction band to trap, which is the exact form or appropriate form for our transitions. We have not thought about that, but yes, the exact form or specific form is really depends on the situation, but that can be a general description on this issue. So can you understand my explanation up to now? So if we introduce a certain defect level, in principle, we have to consider additional equation for trapped charge density, and that is usually trap balance equation. So this is balance equation, or sometimes people call it as a rate equation. So one significant point of this equation is it does not have the transport term. So the electrons does not change its position. Position is fixed as a certain position, and only it changes its species. Previously it was the trapped electron, and now it becomes conduction band electron, or it just remove the hole inside the valence band. So if you have any question, then please let me know. Okay, good. Okay, so then now we can think that, okay, there can be certain state called a trap, and that trap should introduce additional equation. So think about this one. Yes, conduction band, actually it has many different states. However, they are all merged into one single level. And in the case of a balance band, also it can have internally so many different levels, but they are also just merged into single level. Yes, and in the case of trap, they are highly localized, and energetically they can be separated. So yes, here we have defect level 1 or defect level 2 or blah blah blah. So the occupying or occupancy for this trap and that trap can be quite much different in general. So if we are approaching in a most general way, then we have to introduce multiple copies of our trap Late equations. For example, if we have 10 trap states whose energetic positions are different, then we have to introduce 10 different levels. But already we are using just two equations for our conduction band and valence bands. That is enough for our basic drift diffusion model. But if we introduce many states, then now from the viewpoint of a number of unknown variables, now trap has even larger number of unknown variables than conduction band or valence band. So, however, sometimes, really sometimes, these information are this information is really important. So that's the reason why sometimes people willing to pay their computational effort to this one. One good news is sometimes traps are highly localized, and we can consider only the position where traps are important. Of course, trap can located everywhere. So everywhere there can be an average rate of trap density. So, however, depending on the application, for example, importance of this position is much larger than importance of, for example, this one, because it is related with a specific application. So if we introduce certain electron here or certain defect here, will make a much larger impact on additional defect introduced other places. So yes, so sometimes we can just consider small number of trap states highly localized at an important position. So that is the remedy for our computational burden. So let's wrap up today's lecture. Today's lecture was originally intended to give you a really bright trick, smart trick to calculate the terminal current Green function efficiently. However, unfortunately, your homework progress or achievement is not sufficient to proceed this topic. So, instead of talking about the green function, so instead I made a short lecture on the trap levels. So in today's lecture, we have not thought about the specific form of transitions. So just to explain the concept of trap levels and what will happen to our Poisson equation and which equation should be introduced to our drift diffusion equation set, and also how we can modify the conduction. So how can we modify the electron continuity equation and the hole continuity equation? So that was all for our today's lecture. Okay, thank you and see you next Tuesday. Bye.